morning session, the second day of our workshop. So, my name is John Ho Chung from Hamilton University, the neighboring. So I'll be chairing this morning session. The first talk is given by Professor Leon Balents from UCSB. The title of the talk is Quantum Ellipsis Point and a Multipolar Cascade for Frustrated Ferromagnets.
Okay, it's good you applaud before, because by the end, probably no one wants it. I'm not sure if I need this. I'm going to try without, but let me know if you can't hear me. Okay. Oh, great. So, yeah, I want to thank the organizers for inviting me to this very nice workshop. I definitely enjoyed yesterday. There were a lot of really interesting talks about correlated electrons and cold atoms, topological phenomena. This talk is going to be a bit different. I'm going to be talking really entirely about magnetism in insulators. And in fact, mostly it will be a rather theoretical talk, focus on a kind of simple phenomena, well, not so simple, but a phenomena and a model that really has been studied actually for a number of years theoretically in one dimension, and then try to abstract some general lessons from that. I always try to put some picture on the front slide that has something to do with local place and something maybe to do with the talk. So I got a picture of some bubble tea, maybe explain what that. I think the first time I had that was sometime like maybe 12 years ago. I came to Taiwan for the first time and had bubble tea. It has something to do with the talk, so we'll see later. Okay. Really, this talk is a continuation of work with a long-time collaborator of mine, Oleg Starry, from Utah, and there are some aspects of it in which I've been working with a student, Teddy Parker, as well. Kind of the motivation, one of the motivations for this work is, okay, standing here? Better to be over here. I'm right in front of you. I don't know if people can hear me. It's okay? See, you want the microphone. Oh, too bad. All right. Now two-handed is so complicated. All right, fine. Well, my voice will be spared. All right. Good. So as far as motivation goes, part of the interest in this is even though I'll be talking about a rather simple, if you want a toy problem, I think it has some relevance for some experimental systems. We'll talk about that at the end. Part of the motivation, though, is that this toy problem has a lot of rich physics in it, and actually I think we can maybe try to learn something about some of the themes that arise in a lot of much more complicated quantum materials people study lately. These are, to my mind, three of the big themes you hear about when you really go to conferences on quantum materials. Competing phases, we certainly heard some about that yesterday. Quantum criticality, so phase transitions between different quantum ground states and their interesting properties, especially in transport, is a very popular subject these days. And hidden order has been a kind of a subject in correlated materials, especially heavy fermions, for decades, and still arises in materials like recuperates these days. All these systems are really complicated. The one I'll tell you about is, I think, very simple, and so we can kind of understand maybe how these things might be related to one another in this context. So far it's been maybe a little mysterious what I'm actually talking about, so here's the plan. I'll kind of introduce a simple model which has an interesting quantum critical point in it and a surprising number of interesting phases, and then try to describe some general theory for this, which will be a type of unusual type of quantum field theory, talk about what's needed, and then present what we think actually describes it and what we can learn from it. Closer, like this. Yes. Oh, it's so complicated.
This is Asia, you have to get used to that.
Yeah, maybe that's tonight at the party. Okay, the banquet. All right, now it's working? Okay. So let me start by introducing a very simple model. So as I said, this is a model for an insulator. It's a purely spin Hamiltonian. Consider spin 1/2 spins on a one-dimensional chain. These spins will have both nearest neighbor and second neighbor interactions. So this is a kind of J1, J2 chain. And I'm going to focus on this case where the nearest neighbor interactions are ferromagnetic, but the second neighbor interactions are anti-ferromagnetic. So this could be called the frustrated ferromagnetic chain. You could consider this for any spin, but let's imagine spin 1/2. This may seem like kind of a strange combination, but actually it's not that uncommon. Here's a list of quite a few materials which are really described by Hamiltonians of this class. Probably the most famous of these is lithium copper vanadate. If I have time at the end, I'll come back and tell you a bit about the experimental situation in that material. It's a fairly common feature of copper oxide chains which have edge sharing octahedra. It kind of follows from the Goodenough-Kanamori rules if you get this kind of behavior. So what kind of behavior would we expect for the ground state of such a system? So obviously if the ferromagnetic interaction is dominant, it just orders ferromagnetically. As we increase the antiferromagnetic interactions between second neighbor spins, what happens is that frustrates the ferromagnetic state. And at some point, the ferromagnetic state becomes unstable. And then what's known from numerical studies primarily is that beyond a certain fraction, and actually when the second neighbor interaction is 1/4 of the first neighbor interaction, then the ground state ceases to be ferromagnetic, it actually becomes paramagnetic. And there's a very small gap in the spectrum that develops and becomes a disordered state. So if you want a kind of simple semi-classical picture of what's going on, and I'll sort of return to how you should actually apply that later, you can think that as you introduce the second neighbor interaction, what happens is the spins beyond a certain threshold, they actually start wanting to cant. And so the classical ground state would be a spiral whose pitch increases as we increase J2 beyond this 1/4. But it's a 1D quantum system, it can't actually form the spiral state, it does something a little more complicated. So that's the ferromagnet. In fact, it's believed that this paramagnetic state is not really a spiral, but it's some weakly dimerized state. I'll talk about how you can understand that. But what's really more interesting is not the zero field, zero temperature phase diagram, but the finite field, still zero temperature. Everything in this talk is going to be zero temperature. I'll be talking about ground states. On the horizontal axis here at zero field, this is what we had before. There's a ferromagnetic state, and as you increase J2, it becomes paramagnetic. If you turn on a magnetic field, obviously the ferromagnetic state just aligns in the field, and if it's just weakly into the non-magnetic state, it'll take a very small field to polarize it. So there's a whole region up here which is just perfectly aligned spins with the field. But what's interesting is the intermediate regime. It has a kind of low field region, which is something called a vector chiral phase. I'll explain what that is. This is a fairly conventional state. But what's more interesting is this series of states I've labeled 2, 3, 4. So these are what are called multipolar phases. They're rather exotic, and it's surprising that several of these phases appear here. So these are really established results from a lot of numerical and analytical studies, especially density matrix or normalization group. I've just drawn it here because I think it's easier to see in a sketch. So let me try and explain what this multipolar phase here is. This phase I call 2. Here you think about, the simplest way to think about it is, as I've shown in this arrow here, let's start in the ferromagnetic state and reduce the field and ask what state we approach. Okay, so this is the kind of thing you can ask about in any antiferromagnet. And in a typical antiferromagnet, what happens is something like this. Sometimes it's called magnon BEC, magnon, boson-sun condensation of magnons. So if you start in the ferromagnetic state, there's an elementary excitation, which is just flipping a single spin. And this excitation has a quantum number, the field of magnetization along the field of a spin 1. You flip an up spin to a down spin, you change the spin by 1. And now the energy of this state is positive if we're in the ferromagnetic state. There's a gap to flipping the spin. But as we lower the field, the energy of that excitation decreases, and eventually it would cross zero energy. At that point, that means the ferromagnetic state is unstable. That's the point at which you have a transition to another phase. So this spin flip excitation is actually a boson. And you can think about its creation operator as just a spin flip operator, S minus. So when you when you bring this energy through zero, it's like changing the chemical potential of the boson from positive to negative, and at that point, it becomes energetically favorable to add bosons to the system, and they condense. When they condense, you get an expectation value of that boson operator, and that in fact just corresponds to transverse magnetic order in the system. So in a conventional antiferromagnet, when you pass below the saturation field, this Bose condensation happens, and the spin's order transverse to the field. And this happens in many systems, been studied. This is some experimental data for cesium copper chloride, a two-dimensional quantum antiferromagnet. The saturation field here is around 8.5 Tesla. As you go below that point, magnetic order transfers to the field develops, and you can track the TC versus magnetic field. There's a real phase transition there. There's been a lot of studies of this in other systems. Sometimes this can actually occur with increasing field. If the low field state is some singlet state, this is the case in thallium copper chloride, a very popular studied system. Above a certain field, the singlets break up, and again, some spin 1 excitation goes from, I guess these are probably two different experiments. Some spin 1 excitation reaches zero energy, and you develop magnetic order. So in this J1, J2 chain, something else happens, something more interesting. We have these elementary excitations, which are magnons, single spin flips, but they interact. And in fact, in a system with short-range ferromagnetic interaction, they actually attract one another. And so, in fact, there's, due to that interaction, the two spin flips can form a bound state. So it means that the energy of two spin flips can be less than that of two together, can be less than that of two individual spin flips. And so, if we follow the energy of this excitation at high field, of course it'll cost more energy to flip two spins than to flip one. But because of the attraction, as we lower the field, at some point actually these curves cross. And before the spin 1 excitation reaches zero energy, the spin 2 excitation reaches zero energy. And, sorry? How about 3? Yeah, so that's also possible. That's, this depends then on the nature of the interactions. Okay. So, so we have J1, J2. So actually, if we look at the what actually happens here, so in this system, there's a region where you have 2 particle bound states, but not 3. Here you have 3 particle bound states, but not 4. Here you have 4 particle bound states. So let me just focus on the simplest case of 2 for the moment. Okay. So this is analogous to something that happens in ultra-cold atomic systems. You can think about this as like formation of a molecular bound state of bosons. And so this state, when this spin 2 excitation crosses zero, this is like forming a molecular Bose-Constant instead of an atomic group. So in the magnetic context, this is something pretty exotic. It's what's called a spin dematic. So a spin dematic is an example of a kind of hidden order. What's interesting about this spin dematic state is actually there's no conventional spontaneous magnetic order. So if we look at the magnetization expectation value of the local spins, it's uniform, just constant. If you look at transverse magnetization, actually it's zero in this state. Okay. It's not a condensate of single magnons, so there's no expectation value of the creation operator for single magnons. In fact, there's a gap to the creation of a single spin flip still. And so if you look at the correlations of S plus, S minus, they decay exponentially in this. So there's really no conventional magnetic dipole order. On the other hand, if you look at magnetic quadrupole operator, so that single spin transforms like a magnetic dipole, but we can look at magnetic quadrupoles. So we look at a pair of spin operators. This creates a spin 2 excitation, which is actually condensed in this state. So in a spin 2 condensate, you have actually this kind of expectation value, which would correspond to a magnetic quadrupole, sometimes called a spin dematic. It's called a spin dematic because if you think about the symmetry of the system, it's like a nematic in a liquid crystal. So the magnetic field that's applied breaks the full spin rotation symmetry, but we still have rotation symmetry around the axis of the applied field. So that's a U1 symmetry. In an ordinary magnetic ordered phase, we'd have locally a vector spin pointed in some direction in this axis, in this plane normal to the spin. So that would fully break this U1 symmetry. The spin dematic state actually, it chooses a direction in this plane, but not an axis, but not a direction. In other words, if you think about how this S plus operator transforms under a rotation around the z-axis, it rotates by a phase. And this rotates by twice that phase. And so a rotation by pi leaves us invariant. So we would say, in group theory terms, we break U1 down to Z2 here. So more, maybe a nice kind of physical picture for such a state is you can think about it as a quantum fluctuating version of what's called a fan state. So sometimes in spin systems in a magnetic field, the spins will do something which is sometimes called to form a fan or a coplanar state. So if we look in space, a spin might be, here's a field direction, a spin might be pointed here. As I move around in space, the spins will move within a plane containing the magnetic field. Okay. So that's called a fan state. A fan state fully breaks the spin rotation symmetry. But if you imagine now that the spins quantum fluctuate within this plane, so that locally I can't tell whether a spin's pointing here or here, they still would select the plane. So a quantum fluctuating fan state will have all the properties of the spin dematic. So what's remarkable in this very, very simple model, J1, J2 chain, is actually that not only does this spin dematic state, which is already quite exotic, but other phases, this is a phase which doesn't have quadrupolar spin order, but octupolar spin order. This has fourth order multipolar order. I don't know what that's called. There's some word for it. And actually down here, this becomes very difficult to study numerically. There's some debate over exactly what happens here as we approach the zero field transition point. But what seems kind of clear just from looking at this diagram is there's some kind of convergence or a progression of higher and higher multipolar phases as we approach the zero field critical point. So it kind of begs the question, and this is the question I'm trying to ask in this talk, is there some kind of way to understand these phases which unifies them with this zero field quantum critical point? Is there kind of a universal description of that? So this would be a very kind of novel quantum field theory that we would need to come up with to describe all this phenomena together. So what kind of questions might we want to ask? So there are several questions we might ask. We might want to know, is this kind of behavior, so this progression of multipolar phases, is this a generic property of systems which have this kind of zero field transition when we apply a field? So do we always expect this near such a zero field critical point? Is this cascade finite? Does it really stop here at the fourth order multipolar phase, or is there actually kind of a devil's staircase of these things converging down to zero? Can we really have a single, is this too much to ask, is there really a single kind of field theory description that could describe all these phases? As you kind of could tell from this discussion, actually, each one of these phases has a different order parameter. So an ordinary magnetic system has an order parameter, which is expectation of a single spin. That would be actually the case for this lower phase. This phase's natural order parameter is quadratic in the spins. This one is cubic. So to describe all these phases, we need to somehow describe a whole set of order parameters all at once. Can we describe that by one field theory? And is this phenomena specific to one dimension? I don't really have answers to all these questions, but some of them. So what's next, I will actually try to address this theoretically. I'll tell you our proposal for a field theory to describe this, which is a kind of what we call a Lifshitz field theory. It's a kind of nonlinear sigma model. And then I'll go through some of the properties of it. One very nice feature is it turns out that this field theory description actually is actually solvable near this Lifshitz point. So if we're very close to the zero field point, we can do very completely controlled calculations and obtain many exact results. And then we'll move away from this kind of exactly solvable limits and try and understand what we can understand better. Talk about metamagnetism and its endpoint, and finally try to talk about multipolar phases, which is really the motivation. Okay, so let's ask ourselves, if we want to describe, have some kind of universal description of this physics, what's required? Well, there's one very strong constraint on it, which is if we go back to this phase diagram, everywhere in the green region, the ground state of the system is ferromagnetic. And the ferromagnetic state is an extremely simple state. It's a unique quantum state. We can write it down exactly. Just a state with all spins up. And as I vary parameters, anywhere in this region, the state itself doesn't change. So all correlation functions of equal time, anything that's just an expectation value in the state, are exactly constant in there. And so, for example, the ground state energy can't have any divergence as I approach this transition. For equal time correlations, there's absolutely no indication of criticality on this side of the phase transition. So this is very different from kind of usual critical phenomena, classical critical phenomena, for example. You see singularities on both sides of a phase transition. Most quantum critical points also you see singularities on both sides of a phase transition. So this in particular means that this field theory can't be a conformal field theory, which are the ones we know the most about. High energy theorists work mostly on that. This is something different than that. So there may be some people in the audience who know examples of transitions like that. Maybe you do, I don't know if anyone does. There are some known examples. They're all examples which have what's called dynamical critical exponent bigger than 1. So this is I could tell you about some of such examples if you want, but this is a more unusual example. So what we believe is this is described by some kind of nonlinear sigma model. So why is that reasonable? Well, again, we know that the system actually in the vicinity, very close to this phase transition, this is a point we're trying to first describe, very close to this point, it has complete perfect magnetic order. The magnetization is not small, it's actually large. And so it's most natural that we should try to describe the system in terms of a theory where locally there's a lot of magnetic order. We just describe the direction of the magnetization. So this is the reason to use a nonlinear sigma model. We'll write the action in terms of a magnetization, just the unit vector that describes the direction of the magnetization. We'll ignore fluctuations in the amplitude. Well, what else do we know? Well, we know we should have the right kind of dynamics for this theory that would describe properly the ferromagnetic magnons in the ferromagnetic state, which you know in a Heisenberg model, they have a k-squared dispersion like that of a free particle. The way that's described in a field theory is by what's called the Berry phase term. So when we write a field theory, what we're really doing is we're writing a partition function as a path integral over coherent state fields for this ferromagnet. If you do that, you'll end up with the dynamics, which is the same as that you'd have for a single spin, the path integral for a single spin. It would be described by a Berry phase term, sometimes it's called a Wess-Zumino-Witten term, which basically counts the solid angle swept out by the world line of the spin as it makes a periodic orbit on the sphere. And if you can write it out explicitly in terms of this unit vector, here's one way to write it. The most important thing you should note is it has a single time derivative term. This you can kind of guess because the solid angle is dimensionless. The rest of this you can think of as describing the energy of the system. So the ferromagnet has a certain energy density, and then there'll be an energy cost for gradients. And in general, just in terms of symmetry, up to 4th order in derivatives of the field, these are the terms we can write down. And then when we apply magnetic field, let's say along the z direction, we'll couple to this orientation of the magnetization. At the quadratic level, just 2nd order in derivatives, there's only one term we can write down, and so it has some coefficient delta. This would play the role of the spin stiffness in the ferromagnet. It would be positive proportional to the stiffness of the ferromagnet. Actually, as we approach this Lifshitz point, it will go to 0 and change sign. And that's the instability. Classically, remember, the ferromagnet would be unstable to a spiral state. So this instability will be, at least, will be saved. So this thing will, the action should be bounded. So we have a well-defined path integral be bounded by these quartic terms in 4th order derivatives, and there are 2 of them that are allowed by symmetry. We can have basically Laplacian squared and the kind of single Laplacian to the 4th power like this. And so actually there's only really one dimensionless parameter in zero field for this problem, which is the ratio of u and k, and that turns out to be a crucial parameter in the problem. Okay. So one intuition we have is that again near this Lifshitz point, anywhere near the ferromagnetic state, the magnetization. Bless you, Anders. I hope you'll get that taken care of. Is that the magnetization itself wants to be almost uniform. Okay. And it should be very close to the ferromagnetic state, which is actually an exact eigenstate. So we can expect actually that the system should become almost more and more classical as we approach this critical point. So how can we see that? Well, actually it's very simple. You can analyze this thing by just kind of going to non-dimensional variables. We rescale position and time in order to make the coefficients of the fourth order and second order terms the same. So this kind of uniquely determines how to rescale position and time. And if you do this, you end up bringing out an overall factor of square root of k over delta, and everything in the action here becomes basically dimensionless. Coefficient here is plus or minus 1, depending on whether we're to the left or the right of this Lifshitz point. This coefficient we made equal to 1, and then we just bring out this dimensionless ratio of these two fourth order terms, and we measure the field in some dimensionless units of delta squared over k. So remember, this field theory, as always, is a path integral over this magnetization field, and so it's weighted by e to the minus s, and so when this coefficient is very large, we have a very good saddle point approximation. And that's actually the case here. When delta is small, the coefficient of the action becomes very large. So it tells us that actually parametrically close to this quantum phase transition, just the saddle point approximation becomes better and better. So we say that this theory is kind of asymptotically solvable as you approach the critical point. Now you might wonder, does this mean that actually the system is completely classical? So yes and no. It's almost classical, but it's a renormalized classical theory. So if you actually look at this action, contains this term here, which is fourth order in the magnetization. This actually is a quantum term. If we were to analyze the system classically, it would be exactly 0, which is easy to see because the original Hamiltonian is a Heisenberg model, so it's quadratic in the spins. And so the energy should be quadratic in the spins. So you can check actually that this entirely comes from quantum